Okay, before we start example 4, we're just going to recap what we did in the previous lesson. And the first thing we saw is that the constant acceleration formulas can be used with vectors. V equals u plus st and s equals ut plus half at squared. Often with vectors, instead of seeing s used here, you'll see r used here. But r is exactly the same. It's exactly the same as s. It's just a convention that when we're using vectors, we use r rather than s. And both of these represent the displacement from the start. It's very important, and we'll see in this example why, that we bear in mind that it's always displacement from the start. It's not the displacement from the origin. If you've started at a different place, it's not the origin. This will not be the vector from the origin to there. It'll be the displacement from your starting point, whatever that starting point was. Right, so these are true for vectors. We can use them for vectors as long as we have constant acceleration. Meanwhile, there was another formula which we only used when we had constant velocity, which was that r equals r0 plus vt. So this is for when you've got constant velocity. And what that formula does is it shows that if r0 is your start position and you want to know where you currently are after t seconds and you know the velocity, you can do r is equal to r0 plus vt. Okay, and that will give you the position relative to the origin. So that always gives you the position relative to the origin, whereas these two will give you the displacement from the starting position. So let's have a look at example 4, and we'll bear that in mind while we do it. Now, example 4 is a projectiles question. It's a question that you could have done using the techniques from Unit 6, but we're going to do it slightly differently here. We're going to do it, rather than resolving horizontally and vertically, we're just going to do it by looking at the vector quantities and doing it as a whole. Obviously, in an exam, you might still prefer the other method. That's absolutely fine, but it's just going to be a good way to introduce us to thinking about using vectors with these formulas. So let's have a look at the question. It tells us that we are at an initial position of 20j, and that we're struck with 5i plus 8j meters per second, and it asks us to find the speed of the ball 1.5 seconds after being struck. Okay, so to find the speed of anything, we firstly need to find the velocity, and once we find the velocity, we can take the magnitude of that, and that gives us the speed. So to find the velocity, I'm going to use my velocity formula, v equals u plus at. And I'm going to substitute in the values that I've got, and I'm going to do it using our column vector notation. Generally, in these sorts of questions, I think it's easier to use the column vector than the i's and the j's. I think visually it's just clearer what's going on. When we come to acceleration, we actually do know the acceleration in all projectile questions. And this was something we looked at in Unit 6. We said that horizontally in the I direction, there would never ever be any acceleration. It would always be 0. So gravity doesn't slow down how quickly you're moving to the right. The ball would keep going to the right. There would be no resistance there. It would be just keep travelling at constant speed. On the other hand, we should be familiar by now that gravity is an effect of minus 9.8 in the vertical direction. And it tells us that we're looking for the speed 1.5 seconds after it's struck, so we multiply by 1.5. Right, if we add those together, we add the tops together and times the 0 by 1.5, obviously you're still going to get 5. And on the bottom, 8 plus minus 9.8 times 1.5 will give you minus 6.7 to two significant figures. Right, so this is the velocity, meters per second. So to get the speed, I've already said it's the magnitude of the velocity. So we're just going to use Pythagoras on those. This gives us an answer of 8.4 meters per second to two significant figures. Okay, that's part A. For part B, it asks you the position vector, and this is where we've got to be really careful about what the formulas are giving us. Right, it asks you about the position vector r of the ball relative to the origin. So remember, the ball is not starting from the origin, it's starting from 20j. Right, and you can see that marked on the diagram, it's 20 above the origin. So when we use the formula, which we're going to use, it's not going to give you the displacement from the origin, it's going to give you the displacement from the starting point. So if we take a little look here, right, we want to use the displacement formula with my s. But because it's a vector quantity, I'm going to use the r, just because I want you to get used to seeing the r now as well. So we've got that r is equal to ut plus 1/2 at squared. So this is r equals u, which is 5/8, t plus 1/2 0 minus 9.8 t squared. So this is r equals 5t and then 8t minus 4.9 t squared. Okay, that's the position after t seconds of our ball, but this is relative to the start. If we want it to be relative to the origin, we've got to bear in mind that we started from 20 meters above. So if we're going to do it from the origin, we need to take it, then the position vector will be 5t still on there, and it will be another 20 in the j direction, because we started 20 above the origin. So this is our position vector relative to the origin. Okay, so it's quite confusing there. It's just that what we're actually measuring at that point. Are we measuring relative to the start, or are we measuring relative to the origin? So it's always relative to the start if you're using this formula, so we've got to adjust for where we started from. Okay, then finally part C. Let's come back over here and do part C. So for part C, it asks us to determine the distance OB. Okay, so looking at our diagram, if we want to get, and if we're going to get the point at B, what we need to do is, if we're going to find the distance, we firstly have to find the displacement towards B. And actually, what's happened here is that we've already seen that we've got an expression relative to the origin. So if I want to find out the time when it hits point B, this is when the j component is equal to 0. Right? If this in black here is our position with time respect to the origin, then we'll get back onto the floor, we'll get back level to the floor looking at our diagram when our j component is 0. So I'm going to solve that equation. I'm going to put 20 plus 8t minus 4.9 t squared equal to 0. And then I'm going to use the quadratic formula. Obviously that's not going to factorise. And I get two values of t. I get minus 1.362, etc. or 2.995. Obviously I'm not interested in the negative value, it's time, so I only want the positive value, which gives you the time for when we reach the origin. So if I need to find the I component, right, because we already know where the j component is, we know it's on the ground. If we see how much time has gone in the I direction, we can then find out the horizontal distance by substituting that t value in. So this is 5 times 2.995. And obviously we could do that on our calculators, and we end up coming out with, let's see what happens if I do 5.2995. Right, we're going to get 15 meters, and that's to three significant figures. So at that point we know the position that at B, if we've found that it's 15 meters along, so the distance OB from the origin to B must be 15 meters because there's no vertical component, so the horizontal distance is just 15 meters, and that is also the same as the overall distance. Okay, that's it for this lesson, just one example. So you've got exercise 8b to work through, and actually what you can do with that is you can, there's 6 questions to have a go at. I would start with the odds and then see how you feel you've got on with them, and if you need to, you can have a go at the evens as well.